the one thing is that basic electronic structure theory, which is the basic of any computational method, will start from the electron. That would be the Hartree-Fock. That I thought very good. I hope you have enjoyed that lecture. Right now I'm going to the next lecture. So we'll learn slowly these where we have to apply the method. So in my class also, I generally, when I was teaching, I generally always tell to our student that try to learn something. Okay. So in that case, let me teach you where we have to use that method. Probably when I started the electronic structure theory, some of you, of course, you were there, and I also describe very slowly the computational scale, multi-scale modeling method, many things. Their merit and demerit I have to first describe, and then we will go to the other cases. So let's say yesterday when I was discussing this kind of multi-scale modeling method. Why it is called multi-scale, I yesterday very carefully I actually explained. Am I audible? Am I audible?
Yes, sir.
Yes. Yes.
Okay,
Yes.
fine. Okay. So when I was yesterday describing this kind of method and scale, I was telling that x-axis generally represent the length, okay, and y-axis represent the our time, okay. Time means if you look at the when the transition happened of the electron particle was significant, and we will definitely apply such kind of ab initio methods or semi-empirical methods after that, and atomistic simulation method and mesoscale method. The method name was coming. Yesterday I was telling this kind of picture, probably quantum mechanics, molecular dynamics, mesoscale is coming fine. So here, if you look at, we are in the femtosecond range when the electron transition happened in that. Or we are focusing on the electron particle. We generally use either ab initio methods, which are coming in Hartree-Fock, density functions theory. These are the ab initio terms. Okay. Then quantum Monte Carlo, quantum Monte Carlo. There are two types of Monte Carlo: classical Monte Carlo and quantum Monte Carlo. Quantum Monte Carlo will come to the ab initio area, and the classical Monte Carlo will come here, atomistic simulation. Then semi-empirical method. Semi-empirical method, there are many methods. Even till now, I don't know all the names, but similarities like C. Okay, there are many methods. When we are using semi-empirical parameters, there are many semi-empirical methods. For example, one kind of DFT will come in that particular picture. So in that cases, when we are using the scale, is of the order of 10 to the power minus 8 to 10 to the power minus, let's say, 7 in that region. In that cases, we also use some other theory, tight binding theory, and this time scale, if we look of the order of nanoscale, okay, nanosecond. So when we go to the little bit higher, we have to change the method and the scale also when you are increasing the length. Then let's say simulation, when we are starting the especially the let's say lithium ion battery, when the ions we are charging the battery, how the battery is moving inside the ions, sorry, inside the solid state solid liquid interface or in the battery. So that kind of phenomena we generally use the atomistic simulation. And in that atomistic simulation, there are many kind of information. Classical simulation, in that classical simulations we will use the simple classical mechanics. Probably just yesterday Professor Shailesh Kundalwal was describing very well. He was telling that it is really an interesting topic, how to use the LAMP program, atomistic simulation. I think one of our faculty members asking some question, how to develop the force field parameter, that would be in the simulation method agent. So then will come the mesoscale methods, finite element method. Dr. Sumanto Samal will teach probably sometime, and he knows in that cases. And after that, when we have very big scale of the order of meter, then we'll see continuum method, etc. like that. And similarly, I try to define how we should use this such kind of methods and thing. For example, when we apply the this very small, this is basically will come in crystal structure. It is called unit cell, which is highlighted by a box or cube. It is basically nothing but it is just actually cube structure, and we have to apply and focus on the electron, on the quantum mechanics. Then molecular dynamics. Molecular dynamics when will be similar like box, but is a big size. Its name is going to change. Its name is simulation box, not unit cell. And there are probably thousand atoms. We can use the molecular dynamic simulations, and the simulation means how the atoms are moving or kinetic phenomena using just Newtonian mechanics will apply. Or if we don't apply the Newtonian mechanics, we can use some ab initio quantum mechanics or ab initio molecular dynamic simulation. So such a way, we can learn many of our subject about the dynamics, about the quantum mechanics. like that. And after that, when we are going to a group of probably atoms, big molecules, then we apply the mesoscale method. This thing I yesterday described. I want to recap so that the student will, or sorry, participant will realize that what's going behind the subject. Randomly, if I just started from here, then you may feel that probably we may distract. Okay, that's why I'm telling. And when I have the bigger system, we will go to the macro scale system. So every method has some merit and demerit. Okay. In our some courses here, I generally teach many times I taught in our here MTech courses. It is advanced level course here. So in our IIT, most of the courses based on the research. Okay. So in other IITs and other institutes is not teaching in such a way. So whenever we are giving some training to our PhD student, BTech student, as well as MTech student, we give training such a way that they will be interested in such kind of research. It doesn't matter theory experiment, okay? And I am habitual with both theory experiment, but mostly I prefer theory. Experiment you have a lot of limitation. Theory has also a lot of limitation. So basically, what we are doing here when we are giving the training to any student, especially in my class or some other also faculty classes, for example, Dr. Soiles, Dr. Sumanto, Dr. Dubey, we train the student so that they should be motivated in research. Okay, so that's why this maybe someone is attending my class or I already attended in class, he may see the same slide I'm showing, very good. But this is very important to our research purposes. What is that? What is the remedy or what is the importance? So ab initio method in that cases, we generally always use this kind of quantum mechanical or Schrodinger equation, or some cases it will be higher when we have the bigger system called Dirac equation. Instead of just Schrodinger equation, it is non-relativistic. When we'll apply the relativistic Schrodinger equation, then the Schrodinger equation name will be Dirac equation. Okay. So we start from the first principle of quantum mechanics. So it has a lot of important thing. Yesterday I also discussed the most of the perspective of this method is that this using this kind of method will get accurate electronic structure. Will get the mechanical behavior, structural behavior, many other kind of properties also. We can handle such many kind of interesting phenomena. For example, during some kind of metal formation, reaction purposes that involve such kind of phase change, as well as bond breaking, bond formation, and many electronic rearrangement which happen in chemical reaction. We can explain by this kind of density functional theory, ab initio methods like that. And this method offered ways to systematically improve the result. Yes, if we use the Hartree-Fock, the result will be very vague. But if we improve the method, improve the theory, whatever today we are discussing, the exchange correlation and integration part, if we improve such a way, what we'll observe that the result and accuracy will be consistent with the experiment. Okay, so there is a way to improve the method systematically. And systematically we can enhance our data. So similarly, these kind of methods can obtain easily from the exact properties. For example, electronic properties, thermodynamic properties, Raman spectra, IR spectra, many others also. Vibrational modes which they can observe some kind of peak, phonon spectra using such kind of method, and the confirmation also. And there are some difficulties. One of the most difficulties still that now we are in almost close to 2021 year, right? This year still we are suffering many things. Similarly, for example, COVID-19, we are suffering a lot. Not you and me, all of the world economically, health issues suffering. Similarly, at this civilization also we are suffering for the computers. Okay, when we start the calculation, we need too much big cluster supercomputer, many things. But using that set evolution of the order of 100 to 200 300 atom we can consider. I have some system in that cases I have 120 atoms. I remember the density functions theory which I used for some, optimization using supercomputer. It takes 6 months. So there is of course a limitation. Not randomly, maybe 1,000 atom we cannot impose for the ab initio methods. Okay, basically what I to mean that to handle such kind of the big system it is really tough, but small system it is okay. Okay, and of course numerically when we are calculating for quality is very good but numerically is very expensive. Okay, The problem is that it is very fast process, usually of the order of picosecond. That's why when I was studying this kind of information. But when we are going to the semi-empirical methods, adding some semi-empirical parameters, what happened? It is basically simplified version of the first principle methods, which is ab initio method, which only treat the valence electron explicitly, which includes the parameters which is fitted from the experimental data. So probably some of you are habituated with that kind of methods, which is called dispersion additions parameters. We should add there. So basically what happened when we apply such kind of method, we must have to have these kind of parameters, which is the main drawback. If you don't have some experiment, we cannot do that. But it also the similar kind of perspective, like exactly the same thing for the whatever we learn for ab initio same. And more about that, we can handle up to 1,000 atoms. In that cases, time scale is a little bit longer than ab initio method, of the order of few nanosecond we can do that. And also we can get very good accurate data. And the problem is the most difficulty of such kind of method, difficult to assess the quality of the result and trust, who will trust that data. Okay. So basically we have to have some experiment, then we can do that. And ab initio method, we don't need any experiment from theory, we can crack. Okay. So basically we need some information, some input from the experimental or ab initio calculations. Means either we have to complete the ab initio calculation, then do the dispersion, or semi-empirical. In generally, we were doing in such kind of calculation, they do first the ab initio calculation, then they apply the such kind of semi-empirical methods. So atomistic methods that I was telling, that's using some parameters getting from the either data from the force field parameters that Professor Suresh Kundal was telling yesterday. Getting such kind of parameters, they started to do such kind of analysis, which is called force field parameters, which is required for the atomistic simulation, which is maybe semi-classical statistical mechanics to Monte Carlo, determine thermodynamics, transport properties. Many cases we use the exact this kind of exact the statistical mechanical solution to solve it exactly. It has also very good point. In that cases, we can handle the microscopic structure, the microscopic structure, the movement of the atoms, molecules. Some cases people are using this kind of simulation to study our COVID-19 virus, how the virus, some model system are still there. You can see in website in internet that some kind of virus, how we are attacking our lungs. They did some kind of simulations, the motion of this kind of. In these cases, we generally use for the simulations. And I also telling many other cases also we are applying such kind of method to study the protein dynamics, protein folding in material science, metal forming, metal creations, how the metal behaving. We use this such kind of simulation also. For example, metals, we say energy storage devices purposes, how the energy has been stored, how the charged particle are moving. We can also use this kind of atomistic simulations. And of course there are a lot of obstacles over to up to just crossing such kind of after crossing the such kind of over crossing that thing. What we do this Monte Carlo molecular dynamics, this kind of method can handle up to billions of atoms, okay, in supercomputer, and we can observe the movement few microsecond. And the result actually depends. The most problem is that the result will depends how we have developed the force field parameters. That's why probably some of us may ask some question. Only Ms. Paramattami asks that how will get the force field parameter. It is the biggest question. Okay. So force field development, I tried one work. I can give some example. I did one force field development from ab initio methods. For which cases I use the density functions theory to study the porous coordination polymer. Okay, so that force field development I used to do that by my own hand and getting the classical formula. It took 6 months to develop one force field parameter. That's why nowadays people are using already some developed parameter in their library. You can do that, but there is a problem. When you are using this kind of as usual force field parameter, you may observe something X in experiment, you will get data Y in the experiment. So what happened in that case is the quality of the result of course differ from your experiment. So if you have the better force field parameter, you can use this kind of simulations. And another simulation is this Monte Carlo simulation. If we apply the quantum Monte Carlo, of course it's going to ab initio method. It is the more complicated, we cannot do that. I was getting training that quantum Monte Carlo and Monte Carlo in University of California and Berkeley long time, and I learned many things about that kind of things, the how they it works. For Monte Carlo, when you was in classical, the result is going to be deteriorate compared to quantum Monte Carlo. And many physical properties, for example, length and time scale, which will be very inaccessible by this kind of method. And mostly we observe only the energy and kinetic behavior, not the others. So these are the things should be everywhere. Not only here, not only probably this. I would say simulation purposes of Monte Carlo. Many simulation is like that. When we observe such kind of very good phenomena like diffusion parameters, when the ions are moving inside the battery, the diffusion parameters or the diffusion in solids, we can expect from this such kind of such kind of atomistic simulation method. And also some kind of chemical reaction may not be properly defined by such kind of simulations. So in mesoscale method, one of the good thing is that it is the most simplification or atomistic methods to remove the such kind of degree of freedom. And what happened, we have to interacting through the effective potential. It has also very good things that we can use many big and complex cases, and the time scale will be of the order of seconds. We can do the such kind of using, we do not need too much big computer. Even probably normal cluster can do this mesoscale analysis. And we can consider probably 10 million atoms in the system. Of course, when we are increasing in that direction, what happened, the data qualitative data is gradually decreasing, and the data is, or the result whatever you observe in experiment theory, totally just opposite, and it has no such kind of meaning. And the quality of quantitative result may be difficult to really ascertain, means that we cannot confirm this data is reliable. And many approximation limit should be there, that ability to physically interpret the result, means that when you are getting such kind of big system, of course the lot of approximation which is introduced in these cases maybe differ the physical data. And continuum method, it is, we can assume in that case is very good thing that there is no discrete phenomena, it is a continuous, and treat that properties of the system as just field of quantities, okay, just continuous system. And it will be possible to numerically solve such kind of methods already and the good thing is that we can handle such kind of longer system for at least 1 meter 2 meter big meter. For these cases it is required for the industry purposes. And for these cases there are a lot of problem there. You have to give some input, taste sensor, gastric sensor, any input from the experiment you have to put it here, like semi empirical method to a lower scale method, okay. And the result would not be like at the same level what you are observing, and the result will not be trustable, and it cannot explain that can be depend on the electronic and molecular level. Everything now it is happening if you at the level of electronic or molecular level or atomic level. So that level, when you are not reaching the result quality, the data quality is not up to the limit. So there are lots of problem in that such kind of methods. In that cases we defined when we are going to upscale downscale, when we started from the from the lower scale calculation to upscale, the upscale, and seeing other way to downscale. So let's go to the now I will teach. I have just described what is the merit and demerit of such kind of methods, right? So let's see to go to the some kind of application part, okay. So the application part I will try to tell today from here. So one by one we'll go and to the lecture. So approximation of independent particle of the Hardy-Fock method I already described. Many parameters I try to describe. Now let's see go to the real science where we can apply for the the methods. Okay. So now I'm going to my next lecture, which is basically the introduction to the density functions theory. Okay. So now you understand that many methods I described, they are the merit and demerit I have described. Hope you have learned how many methods are there and why then another method is required. Okay. So why the another method is required? It is a big question. Every cases method is required. Why required? It is also very important that previous method has some limitation. To overcome such kind of method, we have to develop a new theory. That is the good thing. Okay. So the another of the one of the thing is that in Hartree-Fock method, we know that if I consider the n is the basis function or number of atoms, if we think that, or number of electrons. So of the order of 10 to the power 4, we can use such. And if you run the Hartree-Fock calculation, you will see with the, if you submit some calculation in Hartree-Fock method, it may be just few, probably just second job, or some cases few minutes. It will be very faster. Then if we apply some other higher method, is let's say Muller-Priestley perturbation theory. Of course, this scale is of the order of 10 to the power 5. And if we use this couple cluster method, it's called post-Hartree-Fock. These are the post-Hartree-Fock method. We will have another course at the end of this month and December. That time I have added some lecture. If you are really interested, I would request to all of you to register this course to learn the post-Hartree-Fock method, okay, and why it is required. And this ACI means configuration integration. If you look at in Hartree-Fock method, we consider the ground state only, single determinant, single stator determinant. But basically in nature, it may not be the only single, might be multi-configuration character. So in that case, it's called configuration integration, multi-configuration. In that case, is n to the power 6 to n to the power 10 time computing time will require to optimize the structure. So what happened? Density functions theory in between them, which method actually is an alternative approach to the electronic structure theory. In that cases, the electron density play central role in the density functions theory. And probably you know Hohenberg and Kohn, they are the pioneer of such kind of theory. They established probably around 1964, and Walter Kohn and Hohenberg, they are and also some Kohn, they say Kohn some theory many will be there. So basically, they actually established considering these electron, these thing. Okay, fine. They tried to consider not that. Let's say we should consider the density of the electron. Okay, so the density of the electron, it would be different than different than previous approach. Okay, and density functions theory is, I already told, is an alternative approach compared to the other electronic structure theory. In this cases, the electron density would be the most important parameter, the central load and density functions theory. And it's not too accurate or not feasible compared to correlated method, which is, I said, couple cluster method. I said couple cluster kind of method is not like that. This is a couple cluster method, not like that, or MP2 or CI, not that. It would be medium quality, but better than Hartree-Fock. And medium and large size small molecule, it not be too much, but it would be for moderate system, medium system, this kind of data would be okay. And one of the good thing I'm telling till now, whatever method I have developed, density functional method is one of the method which provide the accurate or close to accurate geometry, accurate description of the material, accurate description of the nanomaterials and engineering. So let's see the other way, how different, how this kind of introduces the thing. But summary, what we do, Horn and Hohenberg in 1964 published one paper in Physical Review, introduces two theorems. First, they introduce that electron density, which is sum of electronic, external potential sum plus constant term, and total energy of any density is an upper bound to the ground state energy if we know the function of. But mapping is unknown. It's very clear and detailed proof of this such kind of theorem can be found in the electronic structure. I know Richard M. Martin. Richard M. Martin is one of the big scientists who published a book in 2004. You will see that electronic structure. You may get your clear-cut idea with that. So let's see the scale when we are getting the accuracy versus, you may see that this is the accuracy in x-axis and y-axis represent the cost. Okay, so if of course if you want to increase the more accurate data, then you will get the more time and more computer, more high quality computing system, high quality of theory required. Okay, so when we use the molecular mechanics, today or tomorrow I'll show how to molecular mechanics work, and it doesn't take even your computer just fraction of second. Okay, So then you can imagine it doesn't take any time, and your normal computer doing molecular mechanical optimization, that means it's a fake result. It has no importance in science. Okay. Then semi-empirical method, of course, is one is when we're going to the more accuracy, semi-empirical quantum method, then Hartree-Fock method, density functional method, and then post-Hartree-Fock methods. Okay. The MP2, MPN, MP has many things, MP2, MP4, such kind of perturbation theory will come. CI, these are the post-Hartree-Fock method. Here definitely will be another lecture when in December. So many faculty will give most things called post-Hartree-Fock theory and their applications. Okay. So right now I am focusing on this. I described a little bit about the Hartree-Fock method today, and yesterday also some semi-empirical also. Now today I am going to give lecture on density functions theory, and this region I will give a application also. Of course, you have observed that in that slide, that when we are applying the post Hartree-Fock method, which is very the cost is too much. Computationally cost means it is why it is computationally cost means it will require more time and more thing. I would request all of you, if someone is interested, search ACRC, search supercomputer, and it is in IISc Bangalore. You can see the charge. Okay, that is one part of the cost. Let's say if you want to submit such kind of calculation, that supercomputer will take time. Accordingly, IISc Bangalore will take the money from your pocket. Okay, that is called some supercomputer charge. Our cost means we are trying to mean also that cost, as well as how long it will take in that cases, and how much computer power is required to such kind of analysis or calculation. Okay. Similarly, if you do some experiment, let's say you want to do XFS or do NMR, some institutes take long time, as well as some institute offer that thing, they will take money from your pocket. So similar cost, similar concept also here. There is no difference between two us. So now I'm going to the background of the such theory. In 1920, what happened? First, uh, one theory came in market, Thomas Fermi model, which is the introduction of that. Then, after long gap, almost 44 years later, Weinberg and Kohn published one paper which is existence of density functional, exact density functional. After that, 1965, Kohn and Sam introduced a new scheme. It's called Kohn-Sam theory. Okay, Kohn-Sam theory. I will teach today Kohn-Sam theory. And after 5 years, 1970 and early of 1980s, one theory is called local density approximation, which is that time density functions will become more useful. And that time computer means is like a big house. And in that case, it's probably 10 MB RAM. But right now you can see your laptop, your phone has 2 GB, 4 GB RAM. Okay, your laptop has maybe 32 GB RAM. So right now you cannot imagine that technology and today's technology. So technology is rapidly growing. Okay. Now in our probably some cluster here, we have per computing node, we have probably some cases 96, some cases 190 gigabyte, some cases 128 gigabyte RAM. So in that cases, you can imagine 1970 and 1980s, it was not like that. It was more complicated, and computer also is not so powerful. In that time, a density function theory was become useful. In 1985, when I was born, 1985, that time I saw that, sorry, that time it happened. Now I see today. In 1985, incorporation of density functional came to the molecular dynamics picture. He's a big scientist, Carl Partner from Italy. He probably, this is the most popular paper in physical review related, top 10 cited paper, because that time he proposed a density functional theory, which is the development of force field parameter into the molecular dynamics. Okay, so Carpardillo, they are a big scientist in Italy. They proposed that, and that's why the paper in Physical Review dated in 1985. Then 1988, Becky. Becky is one of the great scientists. Then Lee Young Park. Three scientists proposed some functional, which is now very famous, called B3 deep density functional theory in 1988. Okay, Beke Lee Young Pa. Beke. Today when I was teaching the Beke, the Coulomb integral or exchange parameter is coming developed by Beke. Okay, in density functions theory, and Lee Young Pa. developed called correlation parameters. That's why the method name is called B3 leap. 3 is standing for 3 correlation parameters. Our Becky is one, that's a B3 leap. And which is the one of the famous density functions theory when we are using for till now. I would like to tell now, most of the people using for our materials and who are using HOS, they use not a B3. They use always called LDA, like PBE functionals. LDA I will not teach too much. I will teach DFT and I will teach LDA later on. So till now, past it is 2000, let's say 2020, 20, and after 2 months it will be 21. Till now, such kind of density function is not implemented in particular code to study the material. This is the way. Still, it is difficult. Although we have such kind of computer thing, a density function is the most popular in physics, material science, material engineering, and chemistry. After this almost 70 or 70 80-year work, Walter Kohn, okay, Walter Kohn and some got the Nobel Prize when they are awarded to Nobel Prize for chemistry for development of density functions theory. He got the Nobel Prize in 1998 after this kind of Kohn-Sum theory, Kohn-Sum equation development. Walter Kohn is the one of the greatest scientists to develop this thing. Probably you know the later on another scientist there, and I am happy that I was working with his student. His name is John Poppel. Okay, John Poppel was the father of. He's actually he thinks he's mathematician. Basically, he worked for the atomic orbitals and the basis set. Okay, the John Poppel, John Poppel's student was Professor Martin Hedgordon and Professor Lester. I was working with them. John Poppel is one of the famous scientists. Basically, he's the developer of all such kind of atomic basis set. When we are looking for basis set, I will show today what is called basis set, how to define the basis, and these are things. Then it will come to our study today how to use. I think in some kind of slide today, I will show how to define the basis set that John Poppel worked on that. So so in 1990, the Nobel Prize came to the market. Okay, okay, very good. So what 1964 happened? So Hohenberg and Kohn proposed one theorem. What is the theorem? If you look at, I was writing from probably yesterday in the slide. H cap in the Hamiltonian. What is first part? Kinetic energy of the electron. Then electron, and VNE, the potential interaction potential, nucleus and electron, and last term is the electron repulsion and interaction part, whatever. The first part using the atomic unit we are writing in terms of operators minus grad of I square. If we have an electron, we are writing like this way. Very good. Then we are writing this term using a potential. This is the concept. Okay, this is the concept. And the electron part, repulsion part is here. Where the external potential, if we define it, this Vi, which is this. The first theorem Hohenberg and Kohn proposed that the external potential is a unique function of rho r. Where what is the rho r? Rho r I'm not telling. It is a function of something. If we integrate rho r dr over the whole surface or whole volume, you will get the total number of electrons. This is what the first Hohenberg theorem. And Hohenberg, what he did at the same time, from the a row, they are getting two ideas. One is called the potential part, another one is getting the total number of electrons. If we connect somehow them, it will form the Hamiltonian, and H cap psi will get the E psi. But I'm sorry to say that a row later on, I should say, but right now I'm telling to you, a row will be the density of the electron. That's why the method name is called density functional theory. So what happened? The electron density uniquely determined by the Hamiltonian operator, and if we write down the energy of the system is a function of rho, and rho is a function of r, then ENE, the energy of the electron nucleus interaction potential will be rho, and the kinetic energy T is a function of rho, and electron part will be rho. And if we write down in such a way, what we are writing, rho r VNE r dr, which is the first part, and rest of the thing we are writing Hohenberg operators, which is kinetic energy plus electron energy. So what is the first theorem? That external potential is a constant unique function of rho r. This is the first Hohenberg theorem in electronics structure theory. So again, I'm just interpreting in such a way. Say they tried to prove this theorem in the paper. If you go to that particular paper, you will get too much idea about what they did. But here is the summary I would like to propose, that for each electron external potential, there is a unique ground state of electron density. Suppose there are two different potentials like this, of proof is there, but I don't need to prove here because it is well established, and well established method we don't need to too much define here how to improve. The bottom line is that this theorem is already proved, already analyzed, and well established. Okay, so they use the external potential which is corresponding to unique ground state of the density, like that they established. Then using the second theorem, they use the second theorem is basically the variation of theorem. Using the second theorem, they actually tried to calculate the total energy of the system. So the second theorem, what they write to do down, that there is an exist a universal function of FOR, that I try to write in there, such that ground state of energy can be written by, this is the external potential part, and this is the Hohenberg operator, which is universal. If it is universal, then it would be very useful to minimize the energy, and we'll get the ground state of the energy. And using the function, what is the statement which they did, variational principle in density functional theory? The functional that delivered the ground state energy of the system also deliver the lowest energy if and only if the input density is the true at the ground state. Okay, then if we write down the EV external rho, which is this variation by applying the variation principle, it would be less than equal to E0, which is E0 would be the ground state energy. That was the second theorem of the Hohenberg. So using that theory, and variational principle will get for any total for any trial density which satisfied the necessary boundary conditions such a way, the what will happen will get the trial density rho r there, of course, n, which is will be the density of the electron, and if we integrate the rho r there, we get total number of electron. And the energy we can obtain from such kind of a FKH operator represent an upper bound for the ground state energy. Of course, the upper bound should be the ground state energy of the electron. That is the way we work. So what is the summary? If we go to the summary of Hohenberg theorem and today's Hartree-Fock approximation, first one is very good theorem, that if we consider there are many electron and electron interacting systems, the external potential is determined uniquely by the ground state of the electron density. And second case, the ground state energy is uniquely described by on a function which is rho r. Our Hartree-Fock approximation, we have n single electron problem instead of considering the single electron problem, which does not obey the asymmetric principle. That's why Fock operator came, and Hartree-Fock introduced this Pauli's exclusion principle and Slater determinant, which defined the wave function, basically total wave function in the determinant form, and fulfill the Pauli's exclusion principle. Using this theorem, this study, the Hohenberg and Kohn introduced the Hamiltonian density function method just to calculate the ground state of many electrons, and Kohn-Sum equation to calculate the single particle state flowchart of solving the Kohn-Sum equation, like that, H equal to T plus V external. Okay, so this is the basic theory we have studied. Now look at, sorry, I should not. So density functional theory, how we are going to approach. Okay, fine. It is completely rigorous approach. So, and how we can map that kind of system exactly interacting the problem to the non-interacting one. It would be one of this thing approximation. After that, we'll see how this density function is popular. Let's say we have a blue are the all electrons. If we write down this, write down the Hamiltonian part. First part, what would be the nucleus interaction part, whatever we describe. One half is coming just to just to avoid the double counting. And this is the electron nucleus part, which is defined by external potential as per our Hohenberg theorem. Then the kinetic energy of the electron, and this is called the internal part of this electron part. Interacting this particle in a real external problem is like that way we are defined Vxt. Fine. So what they did, we can assume in Kohn-Sum theorem they, let's say this electron, fine, is appearing just only affected potential, which is the quantum system. What we are writing? Only one electron, let's say this electron, we are writing this Hamiltonian, plus this electron is appear, experience some kind of non-interacting potential, which is called effective potential here. But in reality, it is this. But using this quantum approach, this is would be the density function theory, a set of non-interacting electron in the sum effective potential. So basically, if we consider only one, this is fine. If we take the summation, it will be all for the whole system. So in that density functions theorem, Walter, Kohn, and Schramm in 1965, they proposed the density functions theory, and the way they deal is called how to get the electronic ground state energy and wave function. Look at this called, let's say for each external potential there should be an unique ground state. That was the first theorem, and energy can be minimized by minimizing the density functional with respect to the density of the electron. So they wrote like this way in there. I am just copying from exactly from their paper. The ground state energy equal to minimum of E total of function of inner function of, since what is called functional function of a function, that is called functional. So here you will see that the energy is a function of a function. That's why functional name is density functional theory. What is in inside? The total energy should be is a function of density, and density is a function of position. Kinetic operator also will be, electron interaction part will be, and external potential. If there are some ion, so ion and molecule will be interaction energy. So using that cases, this is the quantum approach. They derive the electron density, basically the probability of finding the electron. They define in such a way in a discrete manner. Data would be like this. This would be total, actually total Hamiltonian, getting the which will be the energy. So they are writing in such a way. Is a complicated form. Basically it is the energy, sorry, density. We are writing energy is a function of density of electron. So density of electron is related to the psi star, which is written by here. That's why it is writing like that way. Second bracket, first, third bracket, second bracket, phi I. First part is the energy part. Second part is called the external kinetic energy part. Then the external potential energy part, and last part you will see this is the electron interaction part, and it's called exchange parameters. What happened? The many body electron interaction lumped into the all these exchange correlation parameters. So exchange correlation energy would be one of the concepts. What is the correlation part? Correlation energy, when one electron is here, when the energy of this electron affected by the other electrons, which are motion or static, whatever, that energy should be written by correlation energy. Okay, so you can search what is called correlation energy, and then this is a quantum approach. What about the quantum equation? Quantum equation is very simple. The h square minus 2 omega d square, which is the kinetic part, v nucleus is the potential part, and this is the total we are writing in terms of, this is the electron and is the exchange part. Exchange part basically the change of energy with respect to density will get the single electron. This can be found by, here is the website. You will see that in 1998 when such Nobel laureate was giving lecture, you will get the lecture notes. I copied from the lecture notes, and it is now written many books. If someone needs some books, definitely I am able to definitely give such kind of information to you. So what is the quantum formulation? What kind of calculation going on? So in this is the background we will go. In our theory, in our cases, we don't want to go in detail in that particular direction. So what happened? Let's say we have assumed that we have some wave functions that will get from the geometry, as well as these it's called basis function will give to the computer. This computer will assume that there should be some function, this called exchange parameter, which is function of rho r, which is written by the first cases. Then it will calculate the what is the density of the electron. Okay, let's say we are giving one particular, let's say sodium has 11 electron. So getting this information, sodium atom is 11 atomic number, that means 11 electron it has. And if we define this some kind of basis, we have to develop, which not have to develop, we already it is in our library, and put in the system, automatically it will calculate the exchange and density. Then if we know the exchange, takes the derivative with respect to rho, you will get the exchange correlation parameters, which is exchange potential. Then it will put in the side in the equation here. You can see that what is basically it was the Hardy. If you don't actually, what happened if you don't use this term consum, if you want to put Hardy-Fock in the method, so instead of this exchange it would be the Hardy-Fock k parameters, Fock operator will be there, and it will calculate the energy. If this energy epsilon j single electron, or if you sum all the electron, if it reach to the particular assigned value, then we'll say converge, or it will go to the minimum, it's called converge. Then yes, program will stop the calculation here, convergence is called optimization. If not, it will again go to here and try to minimize the energy. This program is going, it is called iterative method that I was teaching, and it is basically called optimization. And the nature is want to be always optimized, we go to the minimum when, and after that, after getting the optimized structure, which is the biggest question in theory, until you are not having the optimized structure, there is no meaning of other calculation, thermodynamic calculation, molecular properties calculation, electronic properties calculation, mechanical properties calculation. What are A, B, C, D, and we need this. We need the optimized geometry. If you don't have the optimized geometry, there is no meaning of calculation. That in 1965 Kohn-Sum proposed is called flowchart of the Kohn-Sum formalism. Okay, and there is, this is the basically density of functions theory I am done. Now density of functional theory is a sea of subject. And I cannot actually teach just by today night or tomorrow. It is probably big, and many things I also don't know. Many methods every day is developing. For example, Martin is developing the Martin's theory. It's called Head-Gordon functional. Then Minnesota group is Professor Donald Tuller. They are developing some functional and exchange parameter. It's called Minnesota density functional theory. Some cases we say the name. We said today one name B3 leaf. There is called M06L Minnesota density functional theory. There is called PBE Martin Head-Gordon MG functional. In our one Indian scientist, he developed not this density functional. He developed some post Hardy-Fock method. His name is Professor D Mukherjee Devasis Mukherjee from IISER Kolkata. He develops called Mukherjee cluster theory. It's called Mukherjee CCDT functional. In couple cluster, double zeta triple excitation functional. Like that theory, everyday people are developing. Some people are working on still now. So this is the way exchange correlation parameter work for the, I said, for the TFT functional. Now one concept will be there in local density approximation, which is the another density functional approximation, which is not Kohn-Sum. The taking from the Kohn-Sum exchange, which is the most difficult part in theory, we are considering that whenever it is system, it is material, it is molecule, doesn't matter, we are considering it a homogeneous electron gas, and it is the sea of electron. It has some density which is defined by nr, and then we should write down the exchange parameter for each electron, each cases. There is a homogeneous density, which is, that's why we should write out ex is called homogeneous, a function of nr. It's called exchange correlation energy of homogeneous electron gas, and this exchange homogeneous is basically a parameters which is set up by the density functions theory, which is called local density approximation, is this. And using that thing, if we integrate, we'll get the value of the energy using the summing rule. And Purdue and Younger actually they proposed this kind of local density approximation in 1981, and using that kind of summation rule and local density gas approximation, the method is developed. Is called PBE, produced functional. It is called local density approximation. So there are many such kind of density functions theory are available in this system. So you may want, you may not want, can learn more, but up to here is the density functional theory lecture or competition ready. Now probably I'll go to the various kind of application of a density functional theory. In past I used to do couple cluster calculations, Muller plus Muller